Okay, welcome everyone to the second day of the HoTT workshop 2021, taking place in Argentina and all over the world. And we start this second day with an invited talk by Anja Petković Komel from the University of Ljubljana. And her talk is about an elaboration theorem, which is joint work with Andrej Bauer. Thank you very much, Anja, for agreeing to speak. We're very much looking forward to your talk.
All right. Well, welcome from my end as well. So as Benedict said, I'll be sort of a progress towards an elaboration theorem. And yes, this is joint work with Andrej Bauer. I hope he's in the audience somewhere. Okay, so I'll start with discussing what do we think of when we say elaboration. So the first sort of approximation is that we think of adding missing types. So we can start with a rule like this for a lambda, right? And here lambda just has, the body of the function, so to speak. And then what we want to add are the missing annotations, so the types A and B here. And lambda is not the only example. So another one would be the projections of a pair, right? So if we have a first projection, this pair is of type A times B, and sort of the elaboration would add missing type annotations, again, A, B here. And so there are, algorithms that deal with this problem more or less successfully. But I'm not talking about the algorithms per se, I'm talking about what elaboration means today. And I'm trying to convince you that adding missing types is not the only thing that we elaborate. So here's another example. We can also add missing evidence. An example of that would be the termination checker. So we can construct evidence that a recursive function is terminating. And for example, Agda does it. And in Agda, so not every terminating recursive function will have an evidence designed by Agda, right? Agda's algorithms can be flawed. But in principle, that's what we're doing when we have a termination checker. We add some sort of evidence, and then we don't really want to look at it. We just want to know that it's there, right? The user doesn't want to know how the proof of termination looks like. Another such example, familiar, one is the universe levels and their constraints in Coq, right? So Coq adds universe levels and checks that there are no cycles between the levels and so on. And again, the user doesn't want to know about it, but we just want to know that it can be done and that the missing evidence can be produced, right? And elaboration is sort of the process of adding this evidence. So we're adding new information, we're elaborating. So these are sort of the common known examples that you're probably familiar with, but there can be maybe some examples that we could go a step further. And adding missing evidence is not just, for the termination checker and polymorphism, universe polymorphism. We can also imagine things like the following. So we could want to have balanced trees, like AVL trees, for example. And for AVL trees, we know that they're balanced so that the height of the subtrees is at most 1. The difference of the height is at most 1. So we could imagine like a smart constructor for such balanced trees that would, so we would give it the subtrees, and then the constructor would sort of check that this condition holds, and again add missing evidence, so sort of elaborate this construction with the evidence that this is indeed a balanced tree. So we can see that, elaboration is not just adding missing types, but we can also add maybe evidence that something holds. But in general, we could also take it even one more step further and say we would maybe want to elaborate some weird terms. So here I have an example that is not the usual presentation of the natural numbers, but it's a little weird because here we have, the double successor and the quadruple successor, and then the question is, what would we want to elaborate this into? Okay, so in this talk, what I plan to do is give you sort of a general definition of elaboration. And with that, I want to give you an elaboration theorem saying that every finitary type theory has an elaboration. So we would want to know what to do with things like that. And at the end, I'll also discuss some algorithmic aspects of elaboration. But as I'm saying, we first want to just focus on the definition itself, so sort of a precise mathematical way of defining elaboration. And what I'll be presenting today is work in progress. So maybe don't be too hard on me if I don't give you too much information, too precise things. But of course, a discussion is very welcome at the end and in the discussion room after this talk. Okay, so to answer the question, what is elaboration? I'll give you this diagram. So this is sort of our guide throughout the talk. And we start with some finitary type theory. So just imagine any type theory. It might be a little ill-behaved. T here on the right-hand side. And then we want to have a nice theory S and sort of the two maps between them. Okay. So like I said, this is sort of any type theory. We want to construct a nice elaborated theory S and the elaboration map that sort of elaborates terms in T into terms in S. And then we have the retrogression map that sort of forgets the additional information. Okay. And this one will need to have some nice properties. So with this diagram, I will start with explaining what I mean by any theory T here. So as I said, for me, this will be a finitary type theory. So let's take a look at that. What do we mean when we say finitary type theory? So it's a formal deductive system that consists of the following things. So first, we have some sort of a signature of symbols, and we have four kinds of judgments. So that something is a type, that we have a term of a certain type, that two types are equal, and that two terms are equal at a certain type, A here. So here I have these by star things. So the usual way to present it would be without these stars. They're sort of a dummy argument of this judgment. And you will see why I want them, because every judgment kind has a boundary. Okay, we write them as like a box type, box of type A, and so on. And the boundary is sort of, we can think of it as a programmer, I would think of it as a goal to be filled, or, more mathematically, like what needs to be well formed in order for the judgment to make sense. And here you see, yes?
I'm very sorry to interrupt. Some people see the slides later than your audio, your speech, what you say. Mm-hmm. So is there, I'm not sure why that is, if it is their connection or your connection. Would you mind trying plugging in your computer into the cable network?
Mm-hmm. Yes.
Let's see if that helps.
Just a moment.
Some people mention a delay of up to 30 seconds.
Mm-hmm. Okay, that's...
the fact that it's not for everyone might indicate that it's not a problem on your side.
I have this ready, I think. Does this work? You see my screen? No, not yet. Here. Should that be better? Benedict, just a reassurance that you see this?
I see your screen, yes.
Okay. Well, let me know if it's any better.
Okay, thank you.
After a while. Okay. So, right, I was saying we have 4 judgment kinds, and then we have boundaries for every judgment kind. And I said we think of them as a goal to be filled, or what presuppositions need to hold for a judgment to be well formed. And for judgments, we say, well, a judgment is a boundary with a head, right? So here in the box, we put what's in the box as a head of the boundary. And that's why we want to have these stars here with the equation, so that all of the judgments sort of have the universal. I mean, they all look the same. We have a boundary and a head, and we needed some head saying, okay, this equality actually holds, right? So we give it a star. And you'll see sometimes I'll leave out this by star notation when I won't necessarily need it for what I'm doing. So if you just see A equals B without the box, it means by star here. Okay, so these are the judgments, and all of these judgments and boundaries can be put in a context. So this is sort of the context that has variables and meta-variables in them, but I won't be too precise here with the context, but I'm sure you can imagine something under that. Okay, so furthermore, we have all these judgment boundaries and so on, but what we really want is a deductive system, and to do that, we need to have rules, right? So what kind of rules do we want? We want structural rules, so they're the usual ones that are present in any type theory. So the variable rule, the reflexivity, symmetry, and transitivity of equations, conversions, and so on, right? So these are sort of the structural rules for a type theory, and several others. I won't name them, but you can imagine. And for a specific type theory, right, we want to give the specific rules. So we have sort of 2 kinds. We have object rules and equality rules. And here are just examples. So we would say, this is an object rule introducing an arrow as a type, right? And we'd say, okay, if A is a type and B is a type, then A arrow B is a type. Or you have the object rule introducing a lambda. And I intentionally gave you here the not fully annotated lambda, because we can, in principle, give rules of this form. And then we also have equality rules between types, and equality rules between terms. So object and equality rules differ just by whether a conclusion is an equality or if it's an object judgment, as we call it. And these are sort of the rules that are specific to a type theory, right? So if we want natural numbers, we need to give the rules for the natural numbers. If we want to make functions, we need to give the rules to make the arrow type, the pi type, and so on. And of course, we have the congruence rules that are sort of structural rules, but I said that separately because for every object rule, we have a congruence rule as well. So we want to do this. I said they can be sort of ill-behaved, but one thing we do want from this, and this is that the rules have well-formed boundaries, okay? So saying that, the presuppositivity holds. If we have something, then the presuppositions are well-formed. And this is what constitutes a finitary type theory. And of course, we have finitely many specific rules to give for a finitary type theory. Okay, so now we know what any theory means, but as I said before, we have some nicer rules and some not so nice rules, right? And then the question is, for example, which of these two rules is nicer? And I can imagine that all of you already know what I'm going to say. Of course, the nicer one is the right-hand one. And it's nicer because it faithfully records the proof-relevant parts of the premises, right? So basically, the conclusion is some symbol, for example, first here, and it's applied to every premise. Heads of the premises here are given as arguments in the conclusion. And for such rules, we call them symbol rules, right? So the arguments of the symbol, so the conclusion is a symbol, and the arguments are, every premise once. Sort of that's the intuition. And these symbol rules are especially nice, and they constitute a standard type theory. So this is what I call a nice theory S, as we had before in the slide, right? So a standard type theory is such that every object rule is a symbol rule, right? So we don't have things like this that is not a symbol rule, but if we have an object rule, it has to be of this form. It's a symbol applied to some things. And every symbol in the signature has exactly one symbol rule. Okay, and why are these standard type theories nice? It's because they have certain meta-theorems hold for them. Okay, so for example, inversion holds, uniqueness of typing holds, and they're expressible in this Uemura style LF mechanism. Okay, so these are the kinds of theories that we're used to, and they're nice, and we want to work with them. We don't want to work with broken ones with, where the annotations are missing, right? In practice, we always want to say, oh, but actually, we have a standard type theory behind it, and that's our target theory. That's what we're working with. Okay, so elaboration would basically be how we take a finitary type theory here, and we want to produce a nice standard type theory and elaborate into that S with elaboration map, and we have a retrogression map. And this one needs to have some nice properties. It needs to be well behaved. So let's look at what do we mean by these retrogression map. It's a transformation, right, from a type theory S, a standard type theory, into a finitary type theory, so a type theory T. So what is the nature of this R, this retrogression map? We call it a type-theoretic transformation. So first, we transform the syntax, and a transformation of the syntax will have to preserve derivability. Okay, so let's look at that. So we will say that we have a transformation of the syntax if we have type theory U and some type theory T, and for every symbol from the signature of U, we give a well-formed expression in T. Okay, so we map symbols to expressions, and the syntactic transformation will then act on expressions in U, because here we only map symbols, but we can imagine how it acts on expressions to produce expressions in T, right? So we will write F star for the action of an expression, for the action of a transformation on an expression. Sorry. Okay, and then I said it needs to preserve derivability, so that means a type-theoretic transformation is a syntactic transformation such that for every rule in U, so we take a rule in the domain type theory in U, and we need to produce a derivation of sort of the mapped the mapped judgment in T. Okay, so this is what means that we preserve derivability, and we only need to provide derivation of the specific rules, because then the deductive system will take care of the rest. So this is the type-theoretic transformation. And we also said that this retrogression map needs to be well-behaved in some sense, right? Because we don't want to map trivially or some sort. We want this R to have some nice properties. And this nice property that we really want is called conservativity. So this is what means that R is well behaved. Conservativity will sort of give us, we will have, so it will say that S doesn't prove, that S can prove sort of the judgments that T can, okay? So let me be more precise of what that means. We start with a derivable boundary in S. So derivable boundary, it's a boundary and it has a box in it that will make it a judgment, right? And then we map this derivable boundary into T, and by acting on it with, this should be R. By acting on it with R, and we get a derivable boundary in T because we said, R sort of preserves derivability anyway, for it to even be a type-theoretic transformation. So we get a derivable boundary here in T, and then if we can fill this derivable boundary with a head, so if this box has an expression that fits and this judgment can be derived, then, press the wrong slide, press the wrong button, then already the original could also be derivably filled, okay? So if we have a head in type theory T, then the original boundary that we started with also can be filled. And here you can imagine, we can give heads, so we can provide terms for types, or we can provide evidence that an equality holds, right? We can provide stars here as a dummy variable. So this is what it means for the type-theoretic transformation to be conservative. So basically, if we could prove it in T, then we can also prove it in S, but we have to start with a derivable boundary. The question that we're asking needs to already be derivable. Okay, so this is what the retrogression map is, okay? It's a type-theoretic transformation, and of course, it needs to be conservative. That's what we want, right? That's how we want to relate T and S, by having a conservative map, not just any map. Okay, and all that's left to explain in this diagram is the elaboration map L. Okay, so basically this R is the nicer one, right? It's a type-theoretic transformation. It's more syntactic. It has more structure. The elaboration map, well, that one is a bit more tricky because we only want to map what can be derivable in T, right? Because T can have some weird things, and we only want to focus on derivable judgments, on derivations. So this is how the elaboration map will work, right? So this is sort of the essence of what, this is sort of the essence of our elaboration. It's the elaboration map. And what it will do is, if I have something derivable, so elaboration map will take a derivation and it will produce a judgment in S, right? In the standard type theory, in the nice type theory, such that this retrogression map R will sort of play nicely, so it will map it back to the conclusion of this derivation, right? So this is not a type-theoretic transformation as I introduced it before. It's a different kind of transformation because it takes an entire derivation. Okay, so for every derivation, we need to provide a judgment in the standard type theory S. And of course, this condition here gives us that L is a section of R, right? So we want this retrogression map, when it forgets, we need to get the same thing as we started with. So this will be our elaboration. We start with something, we elaborate it, and when we forget, we get the same thing as we started with. So in practice, this elaboration map is what we're after, right? We start with something here, and then we want to elaborate it. We want to add annotations, but we only, in practice, we're only able to do it when we start with something derivable. So this is the elaboration theorem, right? This sort of subsumes the picture I have been giving you the entire time. So here you go. So we are given any finitary type theory T. So for any such type theory, there is a standard type theory S and a conservative transformation R, this retrogression map that we had here, that is surjective on derivable judgments. Okay, so this is sort of the formulation that doesn't really mention L, but we know that this condition is because L is its section. Okay, so, and I said here, see, it says conservative transformation. So the condition that we talked about, that things that could be derived in T can also be derived in S, in a sense. Okay, so when I say elaboration, this is sort of what I have in mind, right? We start with something that maybe needs annotations, is missing some evidence, or is ill-behaved in some sense, it's not standard. And then we want to find a standard type theory and a conservative transformation, okay? So the big question is how to get this standard type theory S from a finitary type theory T. So this is sort of the idea of a proof of this theorem, okay? So the idea is we replace the object rules in the type theory T with symbol rules to get S, right? So I said in T we have some object rules that might not be symbol rules, that are weird, maybe are missing annotations, maybe we have the quadruple successor that we don't know what to do with. And then what we do is, well, we want to make them into symbol rules, into the nice rules, to get a standard type theory. Okay, so this is the main idea. And okay, what are the steps? How would we do this? How do we execute this idea? Well, first step is, of course, we have to define a signature for the standard type theory S. Okay, so for every object rule in T, so maybe I should have this, right? We will start with an object rule in T and provide a symbol rule in S. Okay, so we start with an object rule in T, right? Some object rule. And then for such rule, we'll have a symbol S that corresponds to this rule. Okay, so basically what we're saying is, every object rule will become a symbol rule, so we need a symbol for every object rule. Okay, so step 2 is we can now define the retrogression map, right? Because we said that this type-theoretic transformation, syntactically, right, will just map symbols to expressions. And we already know what symbols of S are. They're, this symbols for every rule, and it will map it accordingly. And what do we want to map it to? Of course, the head of this judgment, the head of the conclusion here, right? So basically, we map symbol to an expression, and this expression will be the head of the judgment of the conclusion, right? So of course, because we want this retrogression map to be a retrogression map, to just forget about the annotations or forget about all the added information, it will have to map accordingly, and of course we'll get this E from R here. Okay, and this will be our retrogression map, right? And now we can act with it on the expressions. And then we also define, so the next step is to define the elaboration map L. And we do this by induction on derivations, right? Because I said, the map L will map from derivations in T into the expressions, so into judgments of S. And we will do it by induction on derivations, right? So just we take an entire derivation and then we can do it by induction. Okay. And then the next step is to give the rules for our standard type theory S. Okay. So again, we want to replace the object rules with symbol rules. So we can only have symbol rules in S. Okay. And of course, we will get to the symbol rules by looking at T. Okay. So we define the signature, we find the elaboration map. So the object rules will be, not surprisingly, the following. So for every object rule in R in T, we have a symbol rule for SR in S. So if we start with some rule R, we get a symbol rule, but okay, I'm being sloppy here a little bit, right? Because here the arguments should be just the heads of the premises, not the entire premises. But you get the idea. So we map with the elaboration map that we defined the premises and the boundary, and then of course the symbol rule will just be sort of the symbol applied to the premises, premises in S, right? So we had to map the premises first. So this is sort of like I said, the idea: take an object rule, make it a symbol rule for the appropriate symbol. Now, what about equality rules? Well, the solution for equality rules is that we get an equality rule, we add an axiom for every derivation of every equality. So basically, we just add all the equalities that we have and throw them in as axioms. So for every derivation of an equation in T, for example, such D, we have an axiom in S, we add it as a specific equality rule. So basically map it with L, act on it with L, and then add it as an equation. And then step 5 is we have to prove the desired properties of R, right? So it actually needs to be a transformation, right? It needs to map derivable stuff to derivable stuff. It needs to be conservative, and given this construction, it can be done, right? So if there's the retrogression map maps a symbol to the appropriate expression, we can use this L that we constructed to prove that it's actually conservative and that it's a type-theoretic transformation. Okay, so this is how we elaborate. This is the elaboration, right? We constructed a standard type theory, a nice type theory, S for our weird type theory T. It's a finitary type theory, but still it can have some interesting things, right? So I gave you an example in the beginning, but I didn't really tell you what the answer is here, right? So now we can sort of guess what will be the standard type theory that will annotate, right, elaborate this type theory. Well, we'll have for every object rule, right, we will have a symbol. So we will actually get 4 different symbols, right? The 0, 1, the S of 0, 1, and this double S and the quadruple S. But we'll also add all equations. Okay. We will also add all equations. So specifically, because, well, one of the equations is the reflexivity, right? So an interesting equation that will appear in our standard type theory after we do the elaboration is that, well, here if I have 2 successors, right? We think of this as a 0 and as a successor, although it's not in the standard presentation of the natural numbers. So if you have two successors, and I add another two, so of this n, for example, I have s of s, and instead of this n, I have s of n, right? This will be equal to this one just by reflexivity, because it's syntactically the same thing. So this will give us an equation in the standard type theory between this symbol and this symbol. So sort of, if we apply this symbol twice, we will get this symbol, right? So we are actually adding some equations that are not just immediately translated specific equations in the initial type theory, in the finitary type theory, but they can occur because of the syntax itself, right? So this is why we get a nice standard type theory on the right-hand side when we elaborate. Okay. Yes, so as I said, all the previous examples, like with the type annotations and so on, should and are examples of this elaboration. So we can, basically when we give a non-annotated term, when we have a lambda term that doesn't have the annotations and so on, and when we add annotations, we're basically mapping from a finitary type theory into a nice standard type theory. And this is what elaboration is, right? And when we're mapping, when we're doing it algorithmically, we're sort of giving the elaboration map algorithmically. Okay, so now we can talk a little about the algorithmic properties of elaboration and what they are. So, like I said, when we think of elaboration as an algorithm, we think of the elaboration map as an algorithm, right? So, the elaboration as a procedure, it takes a judgment in T and gives us a derivable judgment in S, such that the retrogression map maps it back to its original, but only if it exists, right? Otherwise, it reports there is none. Right, because the elaboration map L acts on derivations, right? If we give it something that is not derivable, it cannot give us something derivable in S, right? And that's sort of the thing that's missing when we just say, oh, we have an elaboration map. Yes, it acts on derivations, but in practice, if we want to do it algorithmically, the user will give us something, and we don't even know if it's derivable or not, right? So as I'm saying this, you think, oh, but that's type checking, right? So the question is this elaboration as defined here, so as a procedure, computable or algorithmic? And as I said, yeah, well, it kind of depends if our type theory has decidable type checking or not, right? So what is type checking? So type checking usually means that we check that a term, little a, has type big A, right? This is what we think of. But in our setting, we can think of it alternatively as this. We're checking that the head A fits the boundary box A, okay? And why I'm doing this is because it's a little bit of a generalization, because here, you see, I'm using the boundaries. I'm saying, oh, well, we're checking if a head fits a goal, right? So equality checking is similar, right? We're checking that two types are equal or that two terms are equal at a certain type. But we can express that is by saying, oh, we're checking that the head star fits the boundary A equals B by box, right? So we're checking if this is actually derivable if we put star in, right? We want to check if this judgment is derivable if we put the star for a head. So to combine these two, we can say that we have judgment checking, okay? Judgment checking or boundary checking, I don't know what's a better word for it, checks that a head E fits the boundary B to get the judgment B boxed E, right? And this is the same thing as here, right? We're checking that the term has some type, or we're checking that an equality is inhabited, right? And what we can say about elaboration is that the elaboration is computable if and only if T has decidable judgment checking. Okay, so basically this means that elaboration is the most general judgment checking algorithm for T, if any such exists, right? Because if you can, if you give me a judgment checking algorithm for T, I can give you the elaboration algorithm because I'll just, look at the derivation that you give me and then compute the elaboration inductively by computing L. So indeed, when you say, oh, I'm not really giving you an algorithm for elaboration, I'm giving you an algorithm if you give me decidable judgments checking for the theory you're starting with. Okay, so another thing that also holds is that if T has decidable judgment checking, so does S, right? So the standard type theory S that we end up with after giving you the elaboration will, of course, have decidable judgment checking if T had it, but the converse does not hold. Okay, so we have to be a little careful about that. Okay. Yeah. Sorry, just to check if I wanted to say something else about the slide. No, that's it. Okay, so this is sort of what I wanted to tell you about algorithm. I'm not giving you the algorithm for type annotations for any type theory. I'm not giving you the general algorithm. I'm giving you, algorithm that takes as input the decidable judgment checking algorithm, right? The judgment checking algorithm. And how to implement this is, of course, another question, right? There are several different options for specific type theories that are implemented that does this, right? But in general, it depends if we have such one or not. Okay, so I want to conclude by giving you my Friday's conjecture. So on Friday, Andrea and I were thinking that, and we think this is true, that the map that I gave is the universal elaboration, right? So basically that any other can factor through it. But this would actually, give you why this is a good way of doing elaboration. But as I said, this is still work in progress. So we'll see if this conjecture survives the weekend, or if we'll see if we made a mistake thinking about it. Okay. Yeah, I think that's it. Thank you for listening to me, and I'll be super happy to take your questions.
Thank you very much, Anja. Let's give a round of applause. If I can find the button. Are there any questions that people would like to discuss? There was already a lot of discussion in the chat, but now is the time to ask other questions. I'm not sure I managed to use this Clouder thing, so if you also want, I'm observing the raised hands, but also make me aware of anything, please, if I don't observe you. Mike. Mike, I have admitted you. I hope you can speak now.
Hello.
Yeah, we can hear you.
Great. This is nice. I was wondering about the other direction. So if I start from a nice theory, how many of its annotations can I remove and still have, say, computable elaboration?
I don't know. That's a very good question. I can how much I can forget in order to still have a computable thing. But as I said, the algorithmic properties sort of depend on the type theory. So I wouldn't, at this point, I wouldn't be very confident saying anything about that.
Because from a
So
semantic perspective, right, the nice theory is the one that has a categorical model or whatever. So maybe that's where I might start from, and then I'd like to know how user friendly I can make the theory while still retaining the fact that I can elaborate it.
That's a good question, but honestly, at this point, I don't know. I think Andre is in chat saying something about it. He says, I think Eric Palgrim has worked on this a bit and gave sufficient conditions for removing typing annotations without harm. Okay. Yeah, I don't know that work, but I'll look into it. Yeah, but thanks for the question. That's a very good question. Yeah.
Okay. Joe Wells had a question.
I have an infinite number of questions about this very interesting talk. But I will restrict myself to just one question right now and let other people ask questions. And then if by some miracle there are not a huge number of questions for you, I will ask another question before the session ends. First, thank you very much for this talk. I very much enjoyed it. I wasn't able to follow all of the details, but it I'm encouraged. I hope to watch it again, and I hope to read the corresponding paper. Is there a paper in the HoTT proceedings, or is it just a previous work that you've published elsewhere?
So there is no paper about it yet. This is being written for my PhD.
I want to read the paper.
Yes.
Okay.
Thank you, Joe. I'll make sure that there's a paper, and then I'll give you the reference when it exists.
The paper. I still have some questions, which I've already spoken with Andre or chatted with Andre about during the chat, about why you've chosen not to record details of why the equalities hold in your proof terms. And I suppose that's just because in all of the systems that you're hoping to address, the equality is decidable or not. Am I just confused about that?
Okay, yeah, maybe I didn't give good enough examples. So the equalities can appear as the premises to the rule, okay? But
they don't show up in the proof terms.
Yes, they don't show up in the so judgmental equality. Andre says judgmental equality in type theory is proof irrelevant. So yes, they just appear as a star.
And that's sufficient for all of the type theories that you are addressing so far?
Yes.
Okay. Because I can easily imagine a number of type theories I'm interested in where I don't think that would hold. And I was curious immediately how you would approach that situation. But if you haven't written the paper yet, then probably I'm premature in asking the question.
Yeah, I wouldn't know. Yeah.
Is my mic on, by the way?
Yes, Andre, we can hear you.
But I think you're asking a very general question. You're asking why is judgmental equality proof irrelevant in dependent type theory? That's it, right?
Is it proof irrelevant in every dependent type theory?
For everyone that I know, I've seen a talk by Benno Vandenberg when he was contemplating how one might try to make it proof relevant. I've had discussions with Martin Escardo on the same question, and nobody ever had any conclusive evidence as to how one might do that. It's not an easy question.
And the fact that it's proof irrelevant means that you don't need it for the type inference for finding.
Well, what happens is essentially because it is the only proof irrelevant bit of a standard type theory, then if you want to have a reasonable dependent type theory, you need to be able to recover equations, and that's known as decidable equality checking. Because you've deleted the evidence, you then need to be able to reconstruct it from nothing, which is exactly the meaning of to have a decidable equality checker.
Okay, that was essentially the question I was asking. So basically, you're only so far addressing systems where the equality checking is decidable.
No.
No, we're saying if you have decidable equality checking, then elaboration, then this can be algorithmic.
Right. That was okay. So you're not saying it can be algorithmic in other cases, and you don't yet know how to say what portion of the equality you would need to include the equality proofs you would need to include in the terms of the nice type system?
I think that's two questions now. So first of all,
yeah, probably it is.
right. So I mean, the theorem says, look, so if you have a type theory which has undecidable judgment checking, there is no magic. You cannot make it decidable by elaborating. It's impossible. It's undecidable. So that's the first point. But the second point is,
you could supply part of the proofs. You could include part of the proofs.
No, I mean, if a theory has undecidable judgment checking, then elaborating it won't help. You cannot see, it's already undecidable. It doesn't matter what you're trying to do. It's undecidable.
But it may be semi-decidable. There may exist proofs of the equalities, and you can include parts of the proofs.
Sure. But the point there is, yeah, sure. It seems difficult to do that for judgmental equality, I think.
Okay, so anyway, that was essentially what I was asking about.
Okay.
Thank you very, very much. Someone else should ask a question now.
Yeah, thanks for the question.
How do I turn my mic off? Can't.
Well, just be quiet then.
No. Okay, are there any other questions?
Questions, I have lots.
There's a question in the chat, I think. Carlo is asking. Does Carlo have a raised hand? I don't see it.
He doesn't have a raised hand. I can read out the question for Carlo in his lieu. Carlo is wondering if you can conceptualize the process of going from concrete input to the input to the elaboration map. I'm not sure if I understand the question, but maybe you do.
Yeah, so the process, so it's like a parser, yeah. I don't see how it's different from parsing. I mean, you can parse the concrete input into a finitary type theory and then start with a finitary type theory and combine it, and this would be the input to the elaboration map. So it's basically parsing for the finitary type theory T. There may also be a lot of elaboration that is needed for parsing. Yeah, sure. But yeah, I mean, I'm not, so this is out of the scope of this talk. I'm starting with a finitary type theory that's also already in some sense well-formed, right? It's not nice, but it's well-formed. Andre, maybe you have additional comments on that. I don't know. Maybe I misunderstood the question.
Carlo has another comment.
Go ahead, read it, Benedict.
Unless Carlo misunderstood, it may be very hard for him to go from concrete syntax to a derivation in T, especially if T is very weird.
Yeah, well, yeah, I'm not sure how to answer that.
Okay, well, maybe there is an opportunity for Carlo to join at some point and discuss this, maybe also in the discussion room afterwards. Are there any other questions? Have I missed any raised hands? Please shout out. No? If not, then let's thank Anja again for this amazing talk. Thank you very much. And we now have, so as I said, there is this discussion room open that you can switch to have a less formal discussion. I think discussion rooms are not recorded, if I recall correctly. So people who are too shy to be recorded, they can unleash themselves in the discussion room. And otherwise, we have now half an hour of break, or 35 minutes, and we reconvene, in 35 minutes.
Is the discussion room already started?
Sorry?
Is the discussion room already started? Does it not wait until the precise time?
The discussion room starts, there might be a link already available for the discussion room. Otherwise, at the end of the talk, which will be the official end, will be in 4 minutes and 52 seconds. So Malena has just posted a link to the discussion room in the chat. So if you click on that link, you can go straight to the discussion room. Okay.
I have one question.
Yeah.
When is the dissertation going to be available to read?
That's a very provocative question.
Sorry.
Hopefully by the end of the year.
That question. End of year, Andre says. Great,
yeah.
Thanks.
That's my answer is like hopefully by the end of the year. It says end of the year, so that's when it's going to be. Okay, I'm going to the discussion room now, so we can continue the discussion there.
Okay, perfect. Thank you very much again. See you in half an hour.
Thank you.
Can anyone hear me?
I can hear you.
Yeah, I can hear you. Yeah, sorry, I didn't want to waste a Q&A being clouded. But yeah, I guess, so my question, maybe Mike is right and I misunderstood how you were thinking of instantiating the theorem, but I thought that the T would be like, you know, the version of MLTT that we write in the back of textbooks, like that isn't fully annotated or something like that. And then the question was, you know, how do I go from, like, it's to go from, you know, the thing that I type into my proof assistant to that. Right. Well, figuring out if there's a derivation, I mean, because of.
Oh no, but it's easy to go to the syntax of terms.
If you want to pass to the discussion group, you have to click the
But you
link.
have to know whether the type is well formed, right? In the term. Or sorry, whether the type is well formed, not the term, because that's the boundary of the judgment, right?
Yeah. But then you can use the elaboration, right?
But I thought that I need to know that, like, I need to know that A is well formed to even start doing this elaboration.
I mean, the boundary of A is box type, and it's always well formed. So you can start the elaboration on A, and if you have, you know, decidable judgment checking, then then we'll tell you.
Okay. Okay. So you're saying I'm trying to check. I'm trying to check whether some, like, sort of preterm M is in some preterm A. So I start by seeing whether